Welcome back, Simon. Hello,
Okay.
do you hear us?
Yeah, you need to unmute me.
Um,
Can you
yeah,
hear me?
we hear you well. Yeah, we hear
Oh,
you
okay.
well.
Okay, that's
Yeah.
fine. Okay,
So
good. And can you
welcome
see me
back.
fine?
I hope you had this 15 minutes break and are ready to rock at the next talk. So the mic is
Yes.
yours. Please start.
Okay, great. Thank you very much. Right, so good afternoon, welcome. This session is going to be about Java at speed, building a better JVM. And the idea behind this is to talk about how we can improve the performance of the JVM by doing various different things internally. So the first thing we need to talk about is what we mean by speed in terms of the Java world. And to do that, what I did was I put together a graph which demonstrates the perfect performance profile that we would like from the JVM. Now, this is not talking about the way that the application performs. This is about the way that the JVM performs. Because remember, the JVM is in itself an application. Your application is running on top of it. And the graph that I came up with actually looks pretty simple. So it looks like this. Wow, okay. What we've got there is all we need to do is start our application and have the JVM run at 100% of possible performance and do that for the entire lifetime of the application. So it's as simple as that. That's all we want. That's the perfect world. The problem is that if we look at a typical application, that graph is going to look very different. So it's going to look something like this. Now, if we dig into that in a little bit of detail and see what is actually going on here, well, the first thing is that when we start our application, obviously we've got bytecodes. We compile into this thing, which is a virtual machine instruction set, hence the Java virtual machine. It's not a set of instructions for an Intel processor. It's not a set of instructions for an ARM processor and so on. That's what gives us the whole write once, run anywhere approach to being able to run applications anywhere we want. But that's a bit of a problem because we're interpreting those bytecodes. Each bytecode is taken by the JVM, has to be converted into whatever instruction or set of instructions are necessary to make that bytecode work on the platform we're running our application on. That is an inefficient process from the point of view that every time we see a bytecode, we do the same thing. It doesn't matter how many times we see a particular bytecode, we keep doing the same thing. If we go back to the very beginning of Java's history, that was one of the reasons why Java was criticized for being slow compared to natively compiled languages like C and C++. Obviously, things have moved on, and the developers of the JDK looked around and said, how can we improve this? And they came up with something that had been around even before Java, which was just-in-time compilation. What happens there is that as your code runs, the JVM will keep a track of how many times each method is called. Once a method reaches a certain threshold in terms of being called a number of times, the JVM will identify it as being a hotspot of code, hence the name of the JVM. And at that point, the JVM decides to compile that method into native instructions so it will run more quickly. It does that using what's called the C1 JIT, or as it used to be called, the client JIT. Now, C1 JIT is a compiler that compiles code very quickly. But what it doesn't do is it doesn't optimize that code very heavily. So it will compile the code quickly, but not optimize it. In addition to compiling the code, it also puts in some instrumentation so that as that method is used more, the JVM can also keep a track of how the method is used. So it collects profiling information about that method. When we get to a second threshold where that method has been used even more, the JVM will say, right, now it's time to apply more optimizations to this because it's being used a lot. So it then recompiles that method using a different compiler. In this case, it uses the C2 JIT, or as it used to be called, the server JIT. And so that will apply optimizations based on the profiling information collected and generate much better performing code. So we can see that the code gradually warms up. And as methods get compiled with C2, we get to a higher level of performance. But we do see some big dips there, and that's down to what are called de-optimizations. And the reason for that is that the JIT compiler, using that profiling information, will use speculative optimizations. And a speculative optimization essentially says, we've seen how that method has been used up until now. Let's assume that it will be used in the same way in the future. Simple example, you've got an if statement. Every time we've used that if statement, we've gone through the true branch. So we optimize based on that fact. And we, in effect, ignore the false branch. But at some point, we might get to a situation where we do have to go through the false branch. Our optimization is invalid. We have to throw away the code and then recompile based on going through both the true and the false branches. So that's where we see de-optimizations. We've had to throw away code and then recompile it. Eventually, we get to our steady optimized state. That's our 100% performance because all the hot methods are compiled and they're all running with our heavily optimized code. But we still see some dips in performance, and that's due to something else. That's due to garbage collection, because most garbage collection algorithms pause application threads in order to do the work of the collector safely in terms of marking used objects or moving objects around within the heap. So the challenges that we face with the JVM is that it is a managed runtime environment. That's really good for us as developers because it means that most of the sort of hard work we have to do in terms of memory management and adaptive compilation and things like that, that's all handled by the JVM itself. But in terms of the garbage collector, we have the problem of it being inherently non-deterministic. We can't predict when the garbage collector is going to run. It's not like every 10 seconds the garbage collector will do some work. It only has to do work when the heap space reaches certain thresholds, when we've created enough garbage or we've allocated enough objects, things like that. And one of the problems with that is that the pause times for most garbage collectors can be quite big. And if you're unlucky, you see hundreds of milliseconds. If you're very unlucky, you see seconds, even maybe minutes. And if you're really, really unlucky, the biggest garbage collection pause I ever saw was 1.5 days. So that's the kind of thing that we can deal with. Thankfully, we don't have to do that very often. Second thing is this idea of byte codes and not machine codes. And the whole adaptive compilation strategy has a big impact over how performance works. And again, most importantly, this speed of warm-up, the fact that we have to go from interpreted through C1 compiled code, profiling, C2 compiled code, de-optimizations, and so on, before we get to that optimum level. That time is something that we want to reduce. So what if there was a better JVM? Well, we like to think that there is, and we call it Zing. So Zing is our JVM that we've developed. And what I'm going to do for the rest of the presentation is not give you a sales and marketing pitch. I'm going to explain technically what Zing does. First thing about Zing is that it is based on OpenJDK source code. We didn't want to take a completely clean room approach to developing a totally new JVM. That didn't make sense. Lots of the code in the existing JVM in OpenJDK is very, very good, works very, very well. But there were some things we wanted to improve. So we've done that, and then we build Zing as a JVM. Very importantly, it passes all of the Java SE TCK tests. It's about 150,000 tests for the JDK, and we pass all of those. So what you know is that it is a drop-in replacement for other JVMs. You can simply move your code without changing any of the code, without recompiling, change the directory where you find your Java executable from, and everything will work functionally in exactly the same way. Clearly, it performs better, but functionally, it does exactly the same thing. What we've changed is garbage collection. So we took all the collectors that are in OpenJDK, so the serial collector, the parallel collector, CMS, G1, etc., and we removed them all. And we replaced them with one which we call C4. And I'm going to explain what that is and how it works in a moment. This actually works in conjunction with something we call the Zing system tools. And the important thing about this is it means that Zing will only work on top of Linux. The reason for that is that we looked at how virtual memory system works in Linux, and we decided that because the JVM is a very specific user of the virtual memory system, rather than using the standard Linux kernel one, which is more for general purpose applications, we'd put our own one in there and handle memory allocation and so on directly for the JVM. So because of using that, it's only supported on Linux. Another thing that we've done more recently is replace the C2 JIT compiler with something that we call Falcon. And again, I'll explain what we've done to improve performance using that. And the last thing we've done is to add some technology to the OpenJDK, which is called ReadyNow. And that's about how to eliminate as much as possible this time it takes for an application to warm up. So the time it takes to go through all of these different phases before we get to our optimum level of performance. Just say a little bit more about the Zing system tools. Initially, this was our idea of how to improve memory allocation for the JVM and how we could do some clever things. But what we've found is that with the move to microservices architectures and people wanting to deploy into Docker containers and into the cloud, a lot of people don't want the hassle of having to install extra things on the host operating system. So rather than having to do that, we now have a set of memory management that's built into the JVM itself, uses a different set of system calls, more modern ones from Linux, and that allows us then to avoid having to use the Zing system tools as long as you have less than 1 terabyte of heap. Certainly if you're using microservices, then chances are you're not using 1 terabyte or more of heap for your microservices, although I did come across one customer who was doing that. But anyway, most people will not find that to be a problem. Okay, so how does this work? Well, as I said, we have this new garbage collector, or newish replacement garbage collector called C4, and that stands for the Continuous Concurrent Compacting Collector. Essentially, that tells you exactly what it does. So it's a garbage collector that runs continuously, meaning that we do all of the work in the background and we're able to monitor what's going on. So it's always looking at whether certain things need to be done in terms of garbage collection. It is fully concurrent, meaning every phase of the collection happens concurrently with application threads. There is no need to pause application threads in order to do work of the garbage collector. Having said that, we also are a compacting collector because there are fully concurrent collectors, but they don't compact. This one does, meaning that we can relocate objects within the heap so that we can eliminate fragmentation, we can make sure that all objects are contiguous in memory, and therefore find it easier to allocate space for new objects and so on. From a fundamental point of view, the basics of C4, we use some of the same approaches that you have with other garbage collection algorithms. So first thing is that we have a generational heap. That means we divide the heap into 2 areas, one called young and one called old. A little bit different for C4 is that we use the same algorithm on both the young and the old generation. If you look at like Hotspot, for example, it uses one algorithm on the young generation, one different algorithm on the old generation. We use the same one. The reason we do that, the reason we separate the heap, is because of the fact that if you look at how most applications work, there's a thing called the weak generational hypothesis that says that most of the objects you allocate for your application are only going to be used for a very short space of time. If you can collect those objects very quickly within the young generation, then you reduce the stress on the old generation. So you can make that more efficient in terms of its garbage collection. As I said, it is fully concurrent, but it's also fully parallel, meaning we can allocate multiple threads to the different phases and still have compacting. Really, really important compared to pretty much most other algorithms that are out there. There is no stop the world full compacting phase associated with C4. If you look at things like C1, if you look at things like CMS, at some point they will give up and say too much fragmentation, too fast a rate of allocation. We have to pause all the application threads and do full compaction on the old generation. And that's where you see those very big pauses. We do not do that. So we will just continue to do garbage collection whilst your application runs. The algorithm we use is 3 phases. It's mark, relocate, and remap. Now, how can we do this? Because obviously if we're going to move objects around within the heap and we're going to do marking whilst the application threads are working, how do we do that and make sure that it works completely safely? The reason we can do this is using what we call a loaded value barrier. In effect, that's a read barrier. Every time your application code needs to access an object, it references the object header. What we do is we intercept the reference to that object header, and we use some bits in that header to indicate the state of the object relative to garbage collection, and we know the phase that we're in, so we can look at that and determine whether we have to do some work. That allows us to enforce 2 rules on the references to objects, depending on what the phase is that we're in. So the first thing that we can enforce is that if we're in a marking phase, every object reference that you get will be marked as in use. So that way you don't get accidental garbage collection of an object because we missed it and so we didn't mark it and then it gets collected. Second thing is when you in the marking when you're in the relocation or remapping phases, then you will always get the right reference to where that object is so that you can make changes to it and they won't be lost. So you can do changes to an object even though it's being moved around in the heap completely safely. What people obviously say to me is that if you have a situation where you're intercepting every object reference, surely that is going to degrade performance because now you're doing extra work every time you access an object. The answer to that is, well, yes and no. And why I say that is, well, yes, because we do some work, but essentially all we're doing is looking at a bit in the object header and doing a test and jump instruction. Most of the time, because we've already done what needs to be done, then we don't have to jump to a handler to do something. So we just test the bit and move on. The overhead of that, in terms of the underlying architecture and the CPU, is a single micro operation, so less than a nanosecond of overhead. If you look at the overhead associated with accessing any memory, whether it's through L2 cache, L3 cache, main memory, that's far more significant than anything that we do in terms of our test and jump. The only situation where you might see some degradation in performance is if you only had data that was in L1 cache. And I defy anybody to write an application that does that. So you really will not see a problem with that. If we look at the way that these phases work. So the first of them is the concurrent marking phase. So we need to start doing some garbage collection. And again, we use a similar approach to other algorithms. We need to create what's called the root set. And the root set consists of all the objects that are directly accessible from your application code. To create that, we will scan through the stack looking for references to objects. We'll look at the registers, we'll look at static variables and so on, and find all the objects that you have directly accessible. What we then need to do is obviously mark all of those to say that they are still in use. And then we need to trace from each of those objects to any other objects that they might reference. And then from those objects on until we build up a complete graph of objects that are being referenced by the application and therefore do not need to be garbage collected. So to do that, we take our root set and our garbage collection threads will start working through that, and they will mark in the object header a bit to say this is marked. Then we'll trace through from those and we'll mark the bits in the object headers of any objects referenced by there and trace the graph from there. As I said, we can do this in parallel because the root set actually has independent data. There's no contention in terms of being able to have multiple threads accessing individual objects. So we can do that very nicely and separate it out to parallel threads. Our application threads are running at the same time. So there might come a point where one of our application threads references an object, and this object hasn't yet had the bit set to indicate it's still in use. At that point, we go to our test and jump. And the test will say, oh, hang on, that bit's not set. It will jump to the handler, and the handler will then do the work of the garbage collector, a very small amount, in the context of the application thread, and it will mark the object as still in use. Clearly, we then need to trace objects from there, but we don't want to do that in the context of the application thread because technically that's an unbounded task and it might delay the application. So to get around that, what we do is we pass that object then to the garbage collector and say, make that part of the root set and let the garbage collection threads deal with all of the references. Obviously, if the application then references an object from there, it will do the same test and jump and it will then mark the object if it needs to. So we guarantee, as I said, that every object that you get in your application, if we're in the marking phase, will be marked and we won't accidentally garbage collect it. The relocation phase. So in this case, what we're going to do is we're going to take objects that are spread out through our heap and we're going to copy them and in effect move them to a different place in the heap so that they're contiguous and we can eliminate the fragmentation. I've got 5 objects here, A, B, C, D, E. And we can see that we can very easily move those to a different place in the heap where there's no objects at the moment. So now we have A prime, B prime, and so on, compacting our heap. That's all good. What we then need to do is we need to do that obviously safely. So every time we move one of those objects, we will put a lock around it. Now, sure, that will introduce potentially a very slight pause to the application thread if we're in the process of moving the object whilst it wants to access it. But most objects are very small, and therefore the time it takes to copy an object from one place in the heap to another is going to be very small. So the pause associated with that will be negligible. We then also need to record the information about where these objects have been moved to. And we create a side table for that so that we know that A has been moved to A prime, B has been moved to B prime, and so on. That's the compaction and relocation phase. The other thing that's really nice about what we can do, and this comes back to the idea of the Zing system tools, is we can actually do what's called quick release. And quick release allows us to, in effect, garbage collect the entire heap, no matter how big it is, when we only have one free page of virtual memory for every garbage collection thread that we have in use. The reason we can do that is because obviously in the case of the area that we're moving objects to here, if we look at the bottom part of the diagram, we have our one free page, physical page, mapped to a virtual page, and we can copy the first few objects to that. Having done that, because we keep the information about where those objects have moved to in the side table, we know that from the JVM's point of view, we will never reference object A or B ever again. We've copied it. Whenever the user wants to access it, it's going to go to the new position. So what we do is we can actually steal the physical page from underneath that virtual page and then use that for the next page that we want to copy objects to. And similarly, when we need another page, we can do that. So this is effectively hand-over-hand page reclamation. And so we can use that in a very effective way. Excuse me. So then we need the remapping phase, which is where we need to update the object headers to indicate the new address of the position where we've moved the object to. So again, what's going to happen here is that the garbage collection threads are going to start working their way through the table saying, okay, A has moved to A prime. So we'll update the address in the object header, and then we'll set the bit to indicate that has been updated. So we now know we don't need to do any more work. We can do that in parallel as well. So if we want multiple threads, again, no contention in terms of the object references. Our application threads are running at the same time. They're running concurrently. So at some point, we may get to an object reference which hasn't been updated, but we need to make sure that the application gets the right reference. So again, we'll use our test and jump. In this case, we say, okay, test the bit. Bit's not set, jump to a different handler. That handler will then go to the side table. It will take the information, update the reference in the object header, set the bit so we don't need to do it again, and then pass that reference back to the application thread. So it gets the right reference regardless of where the object is in the heap. If we've moved it, we get the right reference. If we haven't moved it, we get the right reference. So what this means is that we can scale up to very big heaps. We can actually scale all the way up to a 20 terabyte heap, and you will not see any degradation in pause times associated with that. So it doesn't matter how big you make the heap, you won't see pause times increase as you make the heap bigger. That's really good because a lot of people, to minimize pause times associated with GC, will actually divide up work into multiple smaller JVMs and smaller heaps, which then adds a lot of complexity in terms of how you coordinate work on data. Having said that, although Zing works really well with big heaps, it doesn't require them. So we have actually, we now have a smallest heap we support is 0.5 gigabyte. Let's talk a little bit about GC tuning, because this is something that people spend an awful lot of time, effort, and cost in trying to do, trying to get the GC to work as well as possible and minimize pause times. Now, the reason that people spend so long on this is because there are so many options that you can change in terms of the JVM. And so this kind of word diagram here shows lots and lots of things that we have. So there's literally dozens, if not hundreds, of command line flags that you can change the way that the garbage collector, or whichever one you choose, works. And if we look at a couple of examples, these are real world examples from customers we've worked with, and I'm sure people will recognize this type of thing in terms of a startup script, where two different companies have set up Java to run a different application. And I won't go into all the details of what they've done here, but I would just highlight one thing. And that thing is that they both set the survivor ratio, and that's the size of part of the heap in terms of the young generation. One of them set the survivor ratio to be 128. The other one set the survivor ratio to be 2. And so you've got to think to yourself, well, hang on, which is right? Is it 128? Is it 2? Is it 64? Is it 17? It's probably not 17 because that's not an even number. But the point is, that's just one variable. And the only way to try and figure that out is really trial and error. So you try 2, you try 128, you try 64, and you see which one gives you the best performance. And that's fine if you've only got one variable that you need to mess about with. But there's lots of these that you can change. So you end up with almost like an n-dimensional space trying to figure out what's the best set of parameters to give you the optimum level of performance. And it is a true black art to do this. If we look at the same thing with Azul, what kind of set of flags would we need to tune Zing? Pretty simple, actually. All we need to do is set the heap size. Now, this is how we start off with our tuning. We basically say, set the heap size, make sure your application runs, and then reduce the heap size. Reduce the heap size until you get to a point where the system can't quite keep up with it and you need a bit more heap. Turn it up a bit, give yourself a bit of headroom, and that's it. There are a couple of other command line flags we can use. So if we want to sort of tweak things and try and get even better performance, then we can do that. But overall, what we tend to see is that, there's about a handful, there's maybe like 5 or 6 that we typically use to improve performance further. But this is really it. When we start doing performance measurements with Zing, all we do is set the heap size. It's as easy as that. How can I show that this actually works? Well, what we've done is create this little open source tool called JHiccup. And JHiccup is designed to measure the latency associated with the JVM and everything below it, operating system, hardware, and so on. It's not measuring the latency of how quickly your application code can process a transaction. It's looking at how quickly can your application use the JVM, and as a consequence, the operating system and the hardware underneath it. So what we do is we set a thread running alongside your application in the same JVM. But we don't want to mess with your application, so we don't have to interact with it in any way. We don't change the code, we don't interact. And to avoid the problems of actually distorting performance by doing something, we spend most of our time asleep. When the thread starts up, it immediately goes to sleep for 1 millisecond. And when it wakes up, it looks at the system clock and says, well, I expected to wake up 1 millisecond later. What time did I actually wake up? That way, if, for example, garbage collection kicks in whilst it's asleep, that garbage collection runs for 20 milliseconds. When it wakes up, it will be able to say, I woke up 20 milliseconds later than I thought I was, and record that delta. By gathering that information over the time the application runs, we can then generate some log files with histogram data in it, and then we can graph that information to show how an application is being affected by the JVM itself. Let's look at a couple of examples. So this is a machine running Elasticsearch, and we've got a reasonable size heap. We've got a 128 gigabyte heap. What we've done is to run the application using Hotspot on the particular test environment, and then all we've done is to rerun the exact same tests on the same hardware, changing where the Java executable is coming from, so moving from Hotspot to Zing. So the test environment is identical, the load that we're testing with is identical. All we're doing is changing the JVM between the two runs. Now what the graph here shows is the latency associated with the JVM itself. And if we look at the left-hand graph, the one from Hotspot, what we see is a very typical profile that you would expect with this type of thing. We've got lots of small spikes along the bottom there, and those are minor GC pauses. So we're collecting the young generation. Then we've got 2 bigger spikes, and those are major GC pauses, where we're doing some work on the old generation. And as you can see, that happens in a fairly regular way. If we look at Zing on the other side, you might look at that and you might go, oh, that doesn't look very good, because remember, big spikes are bad. So you've got very sort of random looking behavior there. There's no predictable pattern to it. And you've got some quite big spikes there, and it all doesn't look as good as the one on the hotspot side. But I have been deliberately misleading here, because I've actually set the scale of the graphs to be different. If we look at the hotspot graph, that's 0 to 8 seconds, meaning most of those minor GC pauses are going to be about half a second, and the major GC pauses are going to be about 5.5, 6.5 seconds. The Zing side of the graph is 0 to 80 milliseconds. And so if I change the scale of the graph to be the same, what you see is the miracle of Zing. And this is how it works. Basically, we eliminate all of those garbage collection pauses. They just disappear. We get a nice flat line where you have to change the scale of the graph to actually see what's going on. And a lot of that noise that you were seeing on that graph will not be down to the JVM. It'll be down to the operating system doing context switching, hardware, and things like that. We can also do things with small heaps. So this is a Hazelcast node running a 1 gigabyte heap. This time I've used the same scale on the graphs, and we can see that, on this particular example, Hazelcast, we've got a big spike at the beginning doing some garbage collection, and then a very consistent sort of minor GC pause time that's been running there. I would suspect that's not a particularly well set up machine, but even with that, if we go to Zing, we see that completely eliminates all the problems of garbage collection. You don't have to change anything. You just use Zing and garbage collection pauses just disappear. Okay, next thing is the idea of replacing the C2 JIT compiler. And what we did was we said, okay, there are 3 ways of running bytecodes. As I've already explained, we've got the idea of interpreted mode, where things run very slowly. Then we've got C1 compiled code, where, yes, we get a bit of an improvement in performance, but we're not running with heavily optimized code. So we need to compile to get heavily optimized code based on profiling data. And the problem is that it takes time from getting through interpreted C1, C2. So we looked at that and we said, well, improving interpreted, not going to work. Improving C1, well, it just compiles code quickly. We don't have profiling information, so there's not really much to be gained there. Let's focus on C2. And we replaced C2 with this thing that we call Falcon. And that's based on an open source project called LLVM. LLVM's been around for quite a long time. It's a very well supported project. There's people like Intel, Nvidia, Apple, Sony, Microsoft, all have engineers contributing to this project. And it's primarily designed as a static compiler and the sort of back end, which takes intermediate representation and generates heavily optimized code. So we thought, okay, let's use that. And we integrated that with the JVM. So we made it work with the garbage collector. We made it work as a JIT rather than a static compiler. And that gives us a whole lot of better performance in terms of the way we can use better intrinsics. We can do more inlining, fewer compiler excludes, and all sorts of stuff like that. One of the other things that's really good about LLVM is it's very modular in its design, which means now that we've integrated it into the JVM, we can work on lots of different things to add better performance in terms of doing things like escape analysis and all sorts of stuff like that. And of course, every time we rebase from the open source project, we pick up a whole lot of things that people have done and contributed to that project elsewhere. How does this kind of improve things? Well, let's have a look at an example here. This is a simple piece of code which takes an array of integers and then adds them all up. If you give this piece of code to any modern compiler running on a modern processor, it'll say, let's use vector operations to make this more efficient. A vector operation is where you use a wide register, you load up that register with multiple elements of your array, and then you apply a single instruction to it in one clock cycle. So you can do the add all in one clock cycle to all of the elements. So that's a very efficient way of doing things. It's single instruction, multiple data. Been around for a long time. Great. However, if we make that code even just slightly more complicated and we add the idea of a conditional. So now we're adding 2 arrays, but only if one of them's even. Got a conditional, makes it a little bit more complicated. And a lot of compilers, when they're faced with that code, will not be able to recognize it as something that can have vector operations applied to it. So it won't be able to use single instruction multiple data to improve the efficiency of it. And as a good example, if we look at that very piece of code and we say, okay, take C2 and what does it generate as the code on a particular machine? Don't need to go into all the details of this, but the red boxes here show the body of the loop. And what the compiler's done here is it hasn't used vector operations. All it's been able to do to improve efficiency is loop unrolling. And that's a common technique that's used. So rather than doing each element of the array with a separate iteration of the loop, it says, well, actually, we can divide that and we can do 2 elements per iteration of the loop. And that makes things slightly more efficient. Not a great improvement, but it does make it a little bit better. If we look at what Falcon does based on LLVM, it looks very different. Now, you might at first think, well, that looks like a whole lot more code. And technically it is. But what we're now doing is we are using the vector instructions that are available. And on the particular CPU that we had running this example, we're able to use AVX2, which is a 256-bit wide register. What we can also see there, if you look quite carefully, is that there's loop unrolling happening as well, but we're doing 4 elements per iteration. The overall effect of that is that for each iteration of the loop, we're doing 32 elements versus the 2 that it's doing on the C2 code. And many of those are being done in parallel. So the overall effectiveness is very much improved. And this is the kind of thing where, in this case, it's a numerically intensive operation, we can get significant improvements in performance. And that's just one example of what we can do with Falcon. As I say, there's other things we're working on around escape analysis, for example, and better intrinsics. Last thing to talk about is ReadyNow and the idea of warm-up elimination. The reason behind this is that, as we saw from the graph, it takes time to go from interpreted to C1 compiled code, profiling, recompile with C2 or Falcon, and then get to our optimized level of performance. And every time you start the application, you have to do the same thing. So you go through the same process each time. What we decided was, okay, how can we minimize that? How can we avoid that problem? And to do that, we create a profile. So you start your application, you let it run for a while, and you say, okay, we're now fully warmed up. All the methods we need are compiled. We've avoided all the de-optimizations and so on. So we've got our optimum level. Record a profile, and that profile consists of 4 things. It's got all the classes that are currently loaded by the JVM, all the classes that are initialized by the JVM, and that isn't necessarily the same set, all the instruction profiling data that was collected from that C1 compiled code that was fed into Falcon, and most importantly, the speculative optimizations which failed, and we then had to throw away code and then recompile it. We can collect that information over a much longer period of time. So we don't have to just wait like a few seconds. We don't have to wait a couple of minutes. You could wait a week. You could wait a month if you really want to before you collect all that information. And the way that will work is it will then allow us to reuse that information when the system restarts, when the application restarts, and we can then take advantage of that. So essentially what we do is when you start the application again, before you get to your main entry point where we start doing any work of the application, we load all the classes that we can load from that list. We initialize all the classes we can initialize from that list. And then we take all the methods that we know need to be compiled, use the profiling information that we had collected as well, and the speculative optimizations that we know were wrong, and we compile that code so that when you get to the main entry point, you're actually running at about 98% of the performance you had when you took the profile. It literally takes about 2 or 3 transactions just to kind of get to that 100% level of performance. So it really does change the way that your application will start running when it starts up again. Obviously, the drawback to that, if you like, is the fact that we have to do all this work before we get to your main entry point. So there's lots of compilation and stuff like that. What we've now introduced to get around that problem is what we call compile stashing. Compile stashing effectively takes a copy of all the compiled code when the profile is recorded. And that way, because we know that the Falcon JIT compiler is fully deterministic, we can actually say that if we've got the same method as input and the same profiling data, we know that what we're going to get out of the compiler is going to be identical. So that way we can simply reuse the code from the previous run, and we can reduce the amount of time it takes to do the compilation by up to 80%. So that then eliminates a large part of the problem as well. So yeah, fully deterministic compiler. Effect of that, again, looking at the latency associated with an application. In terms of the orange line here, this is before using ReadyNow, so we can see the warm-up where we're doing compilation, de-optimisations, recompilation, and so on until we get to our steady state performance. And then if we use ReadyNow, we've got the blue line at the bottom again, which shows us a nice flat line where we don't have any latency because we don't have to do that compilation. We've already done it, and we've got all our methods ready to run. Just to summarize then, got a couple of minutes left. So the idea behind the Zing JVM is to start fast. So we eliminate the problems of the warm-up phase, go faster so that we can ensure that the application will run with the maximum level of performance, even higher than we would have had with using other JIT compilers. And most importantly, stay fast by eliminating the problems of garbage collection so you don't get those pauses. And that put together gives you the optimum level of performance from the JVM. So you're eliminating a lot of the problems that we saw in the initial graph. It is, as I said, a simple replacement for other JVMs. You don't need to change any of your code. You don't need to recompile your code to make use of it. Just take the same jar files, same class files, and run them with your application. If you're interested in this, you can go to our website. You can get a free 30-day trial. You can install it on your machine. We'll even give you some help in terms of producing some of those graphs, so you can see the before and after effect of the latency, and you can see exactly why Zing makes sense. And so with that, I'm going to say thank you very much. I guess now, hopefully, we've got time for a few questions.
Thank you, Simon. Thank you for 2 talks you did today. That's awesome. And yeah, please don't leave yet. So we welcome you to join the Q&A Zoom rooms. The link was sent to you separately. And dear participants, you can also join the Zoom room with Simon and ask your questions and open the discussion, and just feel free to join and turn on your video and audio. So thank you once again for supporting Devoxx Ukraine online, and I hope we will meet in person next year.
Yes, that would be very nice.
Yeah, thank you.